Ready to the lecture titled In-Band Full Duplex for Wireless Communication Systems. In today's lecture, we will be talking about in-band concept, in-band full duplex concept, explain the transmitter and receiver structure, the key characteristics, the problems facing this new design, and the solutions that can be used in order to mitigate these problems and improve its performance in general. So what's in before we talk about in-band full duplex communication, let's review some of the basic module communication modes we have in wireless systems. First, we have the half duplex communication, where we use it for basically in the downlink and uplink wireless devices. Usually, they can either talk or listen in one band, not in both. And the transmission and reception in these cases is orthogonal in time and the frequency, which means that if you remember with me you have three different types of communication modes. First, the mode we call it one-way communication. Think of that like TV station from from the satellite sending TV signal to your dish at home, or FM base station transmitting a radio signal to your device, whatever, or AM communication. This we call it one-way communication. We have also the listen and talk communication, two-way communication, but you can either listen or talk at one time. And you have the two-way communication where you can listen and talk simultaneously, but using two different bands or two different time slots. So we have these communication modes up until now. The in-band these are the ones that are used in wireless communication systems, and the most famous one is the one we call it full duplex communication, where you have the transmitter and receiver talking with each other on two different bands using FDD, frequency division duplex, or TDD, time division duplex. Now, what's the difference between these communication modes and the in-band full duplex communication? Let's see together what's the difference. In full duplex communication, the two users, the transmitter and receiver, use the same available resource in both downlink and uplink channel at the same time. This means that the transmitter talks with the receiver on the same channel that the receiver talks with the transmitter. So they use the same channel. The advantage here, you can basically double the spectral efficiency, because in one link you are transmitting and receiving simultaneously. Solves the hidden terminal problem. The hidden terminal problem occurs when you have three nodes. Here you have another node, and you want to make sure there is no collision between the nodes when they are transmitting and communicating with each other. So when you use the half duplex mode, transmit or receive, you sometimes encounter the hidden terminal problem, but when you use full duplex communication, you avoid facing this problem because you are simultaneously transmitting and receiving. So what are the other advantages? You reduce the loss in the throughput due to congestion, reduce large end-to-end delay, and you improve the network secrecy. That these are the key 5 fundamental advantages of full duplex communication. But how to extract the advantages offered by full duplex? Two challenges. How to design a working full duplex transceiver in order to make use of these advantages and to realize them in practice. We have to solve the challenges and impairments and drawbacks associated with the full duplex in-band full duplex design. First, we have to be able to design a working full duplex transceiver structure. we need to also know how to utilize the full duplex capability to benefit the 5G need in terms of enhancing the spectral efficiency, the throughput, the network capacity, and serving more users. So the single main problem, the most critical problem that in-band full duplex is suffering from is self-interference cancellation. Let's see how this self-interference cancellation happens. So since in-band full duplex, please let's make it very clear and distinguish between these two terms. We have simplex communication, we have half duplex, and we have full duplex. Now full duplex has two types, out of band full duplex communication, full duplex, in band full duplex. Now what's our lecture is on this topic, in-band full duplex communication, which is the one that's capable of improving the spectral efficiency by 2. It can double it basically. So give me example on simplex: TV, FM, AM, remote control. These are communication in one direction. Half duplex, the devices you see with the police. You can talk or listen at a time. You cannot talk and listen simultaneously. And full duplex full duplex first type, out of band full duplex is similar to mobile phones we have in our hands. You can talk and receive simultaneously at the same, but using either two different frequencies, one for the uplink, one for the downlink, or two different time slots, one for the uplink and one for the downlink. So these are the key differences. Now in-band full duplex, you are using the same time slot, the same frequency for transmitting and receiving at the same time. This is what makes it different from the previous modes of communication, and that's why it can improve the spectral efficiency by double. Now let's see the main problem that in-band full duplex communication suffers from. It's called self-interference cancellation. Why this is a problem? Because when the transmitter wants to communicate with the receiver, the transmitter sends a signal and also receive a signal simultaneously. Let's focus on this side. So the black one here, the black arrow here is the desired signal, and the red part here is the transmitted signal. And as you know, you transmit but also you receive some part. And since the transmit antenna is very close to the physical structure of the transmitter, you receive very strong signal. Yes, the signal is strongest at the point from where the transmitter sends his signal, because as the signal propagates through the air and becomes far from the base station, what happens? The signal degrades. So this is the catch. So now let's go to the mathematical model and see the difference and what are the things we have. So here the source signal XS is belonging to the black arrow, and Xi is the interference signal belonging to the red arrow, and Y is the signal you receive at the transmitter side. At this node, full duplex node, you receive this XS that the user equipment transmits, convolved with the channel corresponding to XS, which is HS, plus XI, the interfering signal, because this is coming back to the receiver. And this Xi is convolved with Hi plus Z. Z is the noise you cannot avoid. So large power difference between the transmit and receive signal. Self-interference signal is generally 50 to 130 dB higher. As you can see, the signal is here 50 to 130 dB higher. Digital cancellation is possible, but invokes a high quantization noise in the signal to the signal of interest. So let's say you need to use analog to digital converter and the quantization to solve this problem. Let's see what happens. You have the signal of interest here in blue, and you have the self-interference. You put them here. The signal of interest here is so small compared to the self-interference signal. And after that, you pass it through analog to digital converter that can perform a quantization. And as you can see, the number of output levels for the self-interference signal is much higher than the number of output levels for the desired signal, and therefore the quality of the desired signal will not be very high. Digitally processing needs analog to digital converter, finite bits of quantization, signal of interest digitized with very few bits. Illustrative example for 14-bit analog self-interference, 15 dB plus only 6 bits after quantization, typical self-interference 50 to 130 dB signal. Higher precision are expensive and slow. This is the problem with analog to digital conversion. Unsuppressed self-interference results in reduced capacity for the full duplex system, which falls below that of the